Hello student, in this video lecture we are going to see another example to develop the flexibility matrix for the beam coordinate as shown in figure. So it is a simply supported beam, okay. So it is a simply supported beam with the three coordinates are shown. So coordinate 1 is moment, then coordinate 2 also moment, and coordinate 3 will be a force coordinate. Okay, let's develop the flexibility matrix for these three coordinates. Okay, so let's start with the solution. The order of the matrix is equal to number of coordinate chosen. So in this case 3 coordinates, so therefore the order of the matrix is equal to 3, n is equal to 3. So therefore the flexibility matrix equal to flexibility matrix is a 3 by 3 square matrix. Okay, F11, F12, F13, F21, F22, F23, F31, F32, F33. So element of this flexibility matrix or displacement. So that is the flexibility. We already know flexibility is equal to deflection by force. We apply unit force, then determine the corresponding displacement. So flexibility, the element of the flexibility matrix or displacement. So first we are going to develop the first column of that flexibility matrix, that is this portion. First column of flexibility matrix, that is this portion, F11, F21, F31. So for this we have to apply unit force or moment in the direction 1 only. Okay, so the coordinate direction 1 is a moment in clockwise direction. So therefore in the first step we have to apply unit moment in the coordinate 1 direction. So that is this one. Then determine the displacement at 3 coordinates direction. So at coordinate 1, then coordinate 2 and coordinate 3. So the coordinate 1 and 2 are moment. So therefore we have to determine the rotation. So flexibility is equal to, so either deflection divided by force or moment by rotation by moment. Okay, so first 1 and 2 coordinates are moments, so therefore we have to determine displacement. Then coordinate 3 is a force, so therefore we have to determine displacement. So for this we may use any method. For simply supported beam it is more convenient to use a conjugate beam method, a moment area method, or whatever it may be. It is more convenient. Conjugate beam method is more convenient. Okay, but in this case I am going to apply unit load method. Okay, so this method, well, we are going to use this method in problems, so that's why I use that method, that unit load method. So you can use conjugate method or Maclaurin's method or moment area method, whatever it may be. Okay, so any of the slope and deflection measuring method can be employed to determine this theta 1, theta A, theta B and delta C. So in this problem I am using unit load approach. So under unit load approach, so deflection is equal to integration of capital M into small m into dx divided by EA. Then rotation is equal to integration of capital M small m dash dx divided by AA, where capital M equal to bending moment due to applied external force, small m is equal to bending moment due to unit load applied in the direction of record deflection, m dash is equal to bending moment due to unit moment applied in the direction of record slope. So first we have to develop the first column of that flexibility matrix, square flexibility matrix. So for this we have to apply unit force, unit moment in the direction 1 only. Okay, so I have to apply unit moment in the direction, first coordinate 1 direction. So first thing, so calculate the bending moment due to external loads only. Okay, the external loads acting on a simply supported beam will be 1 kilonewton meter. So this is applied for determining the flexibility matrix of first column. Okay, the first column of the flexibility matrix is determined from this concept. Okay, so for this we have to apply unit moment. So that is external force applied at support A. Then apply equilibrium equations, determine the support reactions. While applying equilibrium equation, summation of moment about A equal to 0, then summation of V equal to 0, then summation of H equal to 0. Finally we get V is equal to minus 1 by L, Vb is equal to plus 1 by L. Okay, then after that we have to form a table. We have to determine the bending moment due to external force. Okay, so we have to determine the bending moment due to external forces. So for this you can make a table like this. So first column of the table is portion, then second column will be origin, third column will be limit, fourth column will be bending moment due to external force. So split the beam into number of portion. So in this case we have to consider only two portion. One is AC portion, then another one is BC portion. For AC portion, first consider AC portion. So let us consider a section XX, which is x distance from support A. So therefore for AC portion, origin will be A. So limit of that AC portion is equal to 0 to L by 2. So x is equal to 0 at A, x is equal to L by 2 at C. Then determine the bending moment at section XX. So bending moment at the section XX is equal to 1. So we already known the sign convention. Sagging moment taken as positive. Okay, sagging moment taken as positive. So therefore 1 minus 1 by L into x. So one is the one creates clockwise moment, sagging moment about section XX. Then 1 by L into x produces hogging moment. So therefore 1 minus x by L. Then consider another section XX, so which is x distance from support B. So for BC portion, origin is taken as B, then limit is 0 to L by 2. Okay, so x is equal to 0 at B, x is equal to L by 2 at C. Okay, then bending moment at section XX is equal to 1 by L into x. Okay, so this is the bending moment. This is capital M value. Okay, so this is the bending moment due to external force. Now we are going to determine the rotations. Rotation theta A, then theta B and delta C. So first we are going to determine theta A. So for this we have to remove all the external force, all the external load, and determine the bending moment due to unit moment applied in the direction of theta A. Okay, so in the unit load approach, if you want to determine the slope means we have to apply unit force. If you want to determine deflection means we have to apply point load. Okay, so in the first case, first we are going to determine theta A value. So therefore we have to apply unit moment in the direction of theta A. Okay, now we apply unit moment at support A. So it is applied for determining rotation theta A. Okay, so now again apply equilibrium equation, determine the support reactions. Okay, so support reaction is equal to Vb is equal to 1 by L, Va is equal to minus 1 by L. Okay, so again we have to determine the moment due to that unit moment. Okay, so for this we have to make a table like this. One is portion, first column is portion, second column is origin, third one is limit, fourth one is bending moment. Bending moment, that is M dash, MA dash. Okay, So first consider AC portion. So let us consider section XX, which is x distance from support A. Then origin of that AC portion is A, then limit is 0 to L by 2, then bending moment 1 minus x by L. Then consider BC portion, origin is B, then limit is 0 to L by 2, bending moment is 1 by L into x. Then theta A equal to integration of by unit load theory, unit load method. So theta A is equal to integration of capital M small m dash into dx divided by EA. So substitute m and a small m dash value. So first for AC portion we have to first apply in AC portion, then BC portion. Okay. So for AC portion, so limit will be 0 to L by 2, capital M is equal to 1 minus x by L, small m dash is equal to 1 minus x by L into dx divided by EA. For BC portion, again limit is 0 to L by 2, capital M is x by L, small m dash is x by L, dx divided by EA. Then integrate this equation. So finally we determine theta A is equal to L by 3 EI. So F11, the flexibility, the element of the flexibility matrix F11 is equal to, so equal to theta A, which is equal to L by 3 EI. Okay. So F11, so 1 is now we are going to determine theta B value. Okay. So for this again remove all the external load, determine the bending moment, determine the bending moment due to unit moment applied in the direction of theta B. So second coordinate direction is anti-clockwise moment, so therefore we apply anti-clockwise moment at B. Okay. So now determine the support reactions. Okay, so V is equal to 1 by L, then VB is equal to minus 1 by L from equilibrium equations. Then determine the bending moment, that is small m dash value, small m dash value. So for this you have to make a table like this: portion, origin, limit, bending moment. First consider AC portion. So origin is A, limit is 0 to L by 2, bending moment is equal to, this is our section, bending moment is equal to 1 by L into x. Then again for BC portion, bending moment is equal to minus 1 minus 1 by L into x. Okay. Then theta B is equal to integration m dash dx divided by EA. So substitute capital M, so bending moment due to external loading, then small m dash into dx divided by EA. So after integrating this term, finally it gives theta B is equal to L by 6 EI. Okay. So therefore F21 equal to theta B, which is equal to L by 6 EI. The direction of theta B and coordinate 2 are same, so that's why it is taken as positive. The next we have to determine delta C. So for this again remove all the external load and determine the bending moment due to unit load applied in the direction of delta C. So remove all the external load, so apply only unit load at the mid span. Then determine the support reaction. Due to symmetry, support reactions are of 1 by 2, 1 by 2. So then again determine the moment. So for this again make a table like this: portion, origin, limits, then bending moment. Then finally delta C is equal to integration of capital M small m dx divided by ei. Substitute capital M and small m corresponding to each portion. So, finally integrate this term, which gives delta z is equal to L square by 16 EA. Then finally F31 flexibility, the element of the flexibility matrix is a displacement. So, in the third coordinate is the force coordinate, so therefore we determine displacement. So, F31 equal to delta C equal to L square by 6 EI. The direction of displacement and coordinate 3 given are same, so therefore it is taken as positive. Okay. The next, apply the same procedure for second and third column of matrix.